surface integrals, and in particular we're going to focus now on the flux. That's a surface integral of a vector field over a surface, and this is the formula that we're going to use. S is the original surface and D is the projection of S typically onto the floor, to the XY plane. So this one is a version equation 7. Pretty simple, relatively speaking, pretty simple vector function. Z, which describes the surface, is this fella, and it's between Z equals 1 and Z equals 2. So if you imagine this surface, but they cut it. Actually, I believe this is a cone, and they cut it a height of 2 and a height of 1. So one of the things I'm going to do here right now, is find out what D looks like. Well, we know that Z is this guy. And we're told Z equals 1, which gives me this guy. But if you rearrange that, isn't it the same as saying that? And then if we take Z equals 2, we get this guy. So basically, this surface cut from Z equals 1 to Z equals 2, and then you project it onto the floor, you are essentially looking at a donut. And the inside radius is 1 and the outside radius is 2. Are we cool with how I figured out what D was? Basically, you want to see what the surface would look like if that surface was, I guess, shown on the floor, right? What would its silhouette be if it was on the floor? So now that I've got that guy set up, let's do this piece. The flux, which is what this is called, is going to be the double integral. Just looking at that, would you say not a problem, polar? Would you agree polar is the way to go? So why don't I set that up and I'm pretty comfortable with the polar version of what that looks like. Right, so I don't think it should matter, so I'm going to do R first. Going to do theta second. And then we've got this ugly mess, and it truly is ugly. That's P, this is Q, and this is going to be R. So it's, God, this is messy. I should have planned ahead and shifted this a lot to the left, but it's too late now, so I'm just going to take it as it comes. It's going to be negative P, which is the negative of this guy, followed by the derivative of G with respect to X. So I guess I should do that down here since I do have some room for it. We're going to do the partial derivative of this with respect to X. In order to do that, I'm going to have to call it a half power. So the partial derivative with respect to X is a chain rule of 1/2 x squared plus y squared to the negative 1/2 times the derivative of x squared plus y squared, which is 2x. The 2 and the half cancel and you get an x, and that guy ends up being x squared plus y squared on the bottom. Can we just, we go with that. I skipped a couple of lines, but that's what you get. So this is going to be x over the square root of x squared plus y squared. That's the first one. Now we do the second one. It's going to be negative q times the derivative with respect to y. Well, can't I just use symmetry here? So if I was doing this with respect to y, I'd get a y over the square of x squared plus y squared. Then I'm going to add r, which is technically z cubed. Agreed? But z cubed is that guy cubed. And the whole thing's going to be done with an r dr d theta because we decided to go polar. So the flux filler is, let's see, theta equals 0, theta equals 2, r equals 1, r equals 2. All of that gets you x squared. All of that gets you plus y squared. This guy here, essentially all this guy here gets you is, I guess I'll just leave it as x squared plus y squared cubed for the time being. Can't think of a better way of writing it yet. If you're not on top of it, you might not notice something that I can do to these two guys. Because, I want this thing to be as simple as possible, because if I'm going to integrate it, ugly is not good. What can I do?
Fractions.
Combine them. Yep. And if I combine them, and I'm just combining these two, I'm not even thinking about what the heck I'm going to do to that yet. This can be simplified. Agreed? What can it be simplified to then? What does it become when you simplify it?
R squared over the square root of r squared.
Oh, you went that way. And if you did r squared over r, wouldn't you just get r then? And totally cool with that. I'm just going to do that. Can't you take a half power out? Okay, now you've already noticed that. Isn't this guy r? Isn't this guy r cubed? And so, yeah, it was really ugly, but isn't it nice in polar form? Are these variables separable? So I want to do 0 to 2 pi of 1 d theta. I want to do 1 to 2 of essentially that guy. And can I dot it now, because it's pretty well done. So if we got an answer, let's pretend it's 42, and this particular situation was a surface, and the vector field was actually describing a vector which is the light projecting out of it. The flux, which is this number 42, would be saying this object would be having on average 42 lumens per square inch. But how bright it would be, I guess. I tried to be an engineer there. I'm not sure it worked, but just so that you've got a feeling for what you're doing. Okay, now the next question, I'm just going to set up. I'm not going to take it as far as I did that one, even although I didn't finish that one. And this is a version of question 8. We're doing the flux thing, right? Okay, in question 8, I never think clever places to put this. There's F. And F is just basically a Y, a negative X, and a 4Z. And the surface S is given by X squared plus Y squared plus Z squared equals 4. And they tell you that Z is greater than or equal to 0. So if you imagine what that would be, can you imagine in 3D space? Oh God, forget it. It's the top half of a sphere. Right. So I need to get some pieces here. I need to figure out who D is. Now, if you take this surface and you project it down onto the ground, aren't you just making Z 0? That's what XY plane is. So when I do that, do you see it ends up just being a very simple circle? And so that tells me I'm going to go polar. So I can go up here and do R equals 0 to R equals 2, theta equals 0 to theta equals 2 pi. And then basically this guy, and this guy. So negative x, negative p, should call it what it is. In this question, your p, your q, there you are. So it's the negative of y times the derivative. Oh, that's an interesting problem. When we try and find the partial derivative dg by dx, it's the same thing as finding that, agreed? Z is just g, right? I could rearrange this and I would eventually get what we're looking for. And if I did, can you see it's going to be a really ugly square root? So since I'm only setting this question up, I'm not going to take it the whole way. And since it's positive, I know I'm only going to use the positive square root. So can you imagine, I'll just put that in as a placeholder. You differentiate this with respect to x, you'll get whatever ugly mess you get, but you will get it, right? And that will go there. And then you take away the next one, so take away negative x, and you'll do a dz by dy. And then you'll add an r, which is 4 z's, which means you'll add 4 of these guys. Technically, dA. So ugly guy, a whole load of things with x's and y's. But since we're doing polar, can you imagine, for instance, that this guy here, for instance, won't he end up being that guy? And don't be surprised if there's an awful lot of x squares plus y squares and things like that floating around. But that's as far as I want to take that one. So you've got a lot of work to do to get it to a place where you can get the answer. I'm just looking at a solution. Believe it or not, it might not look like it, but it does end up becoming, according to what I've been looking at, it becomes that. So it might seem unlikely, but this whole mess ends up being just r square root of 4 minus r squared. I'd like to have seen that one. Oops, wrong one. 12. There we go. And f is nothing that spectacular. It's got an xy in it. It's got a 12x squared in it. It's got a yz in it. Okay. And what do we know? Oh, we know z is x e to the y, so you basically told me what she is. And you're being told, because they're being really nice to you, that. So in this case, I don't need to worry about d. Isn't that d? So I know my integral is going to go from, say, y equals 0 to y equals 3. And from x equals 0 to x equals 3. And then I just basically put these fellas in. I'm not sure if I've got enough room, but I'll try.
The x should be going from 0 to 1.
Oh, thank you. So we stick a negative in front of this guy. And then we differentiate this with respect to x, which gives me that guy. Then you take away the next one, and you do a q, which is this fella. And you differentiate this with respect to y, and you get x e to the y. And then you just add r, which is this fella. I think I'll take this a little bit further. So it's 0 to 3, 0 to 1. I've got this term, oops, that's a negative, subtract this term, add this term, and I'm doing x's first, right, and y second. Right. Let's look at this horrible mess. Assuming I didn't skip anything. How are we going to tackle it, I guess is the question. Now, I was home, and if that dan y wasn't there, I would have done it, that I could have done a variable separable.
Shouldn't there be a y on the last term?
Oh, this one? Oh, that would be nice if there was.
Because r is yz, not xz.
Then I take it back. Right, this is the guy that we got.
Shouldn't it be x e to the y, x e to the y? Because z is equal to x e to the y.
Okay, z is this guy. Okay. And so I should be doing r, which is this fella. And r should be that. There we got it. Took me I don't know how many times. Now I looking at it, and I am actually nice and surprised. Though I couldn't figure out what the heck that was, it's actually variable separable. Won't this kill off that? Negative xy, positive xy. So how about from 0 to 3 of e to the y, and 0 to 1, that guy. Dot, dot, dot. Yeah, I was going to go some really bad place there. Can I just tell you what I would have done? Can we imagine that that was what was left over? What technique would I have done? Well, I could have separated out the x, but wouldn't I be left with the y e to the y? So what method would I have used if I had to deal with a y e to the y?
Would have had to been integration by parts.
Right. So that's where I thought it was going. So my brain kind of almost like wanted me to make sure that I had that. But in effect, they killed each other off, so they disappeared. Will you lot say hi right now? Get attendance. Excuse me. Okay. Just check this out. Oh, I was one of the reasons I wasn't quite ready. Excuse me, a little bit late. Was I had to go and observe someone teaching online, and it came up with something that I wasn't aware of. You lot, when you see my white screen, you should be seeing the full screen covered in that, not a little small picture. Are all of you aware that you can make that happen if it doesn't happen automatically? Right. Now, if you didn't know how to do that, do you know you just click on it and there's a thing that says pin to screen or something? Yeah, because it's, what's the word I'm trying to say? When I am teaching online and I'm seeing something, I have to be really careful that you're seeing what I'm seeing, because I know sometimes I'm talking away here and I'm seeing exactly what's happening, but you're seeing some other picture. So your job, as you're pretty good at it, is to tell me that, you know, hey, I can't see what you're seeing, or it's not. And I know that most of the time I probably bore you by saying, are you all now looking at? But I found out from that lesson that it's a very good thing to do, because when you see it from the way you lot see it, it's quite a different experience. Okay, so let me show you what the heck's going on here. We did one of these last time, but I'm not really sure that seeing one is enough. But I don't want to do the whole question because then you won't get any practice. So in this question here, it's back to just a normal guy. If you can't remember, what do I mean by the normal guy? I mean this fella. You see the formula's quite different when you just find a surface integral, right? When you're not finding a flux. And the main difference is that the function f is not a vector function, right? It's just a 3D function, right? You plug x, y, and z in and you get a number. And these three guys here, somehow or other, these three guys here are going to be used in calculating this. And d is the projection of this onto the floor, essentially. Right. So we have two jobs. First job is we need to find z equals function of xy. And the second job we need to do is we need to find out what d looks like. Let's look at the second job first. If you want to know what these 3 points, which basically form a triangle, what these 3 points look like when they hit the floor, don't you make the Z coordinates essentially disappear? So this point would end up at 1, 0. This point would end up at 0, 8. And this point would end up at 0, 0. Does that make sense? If you wanted to know what this triangle floating in 3D space would look like, you're taking the 3 corners and you're saying, okay, what's their X and Y coordinate? Because that's what I would say on the floor. So this guy becomes 1, 0. This guy becomes 0, 8. And this guy becomes the origin. And that's what D looks like. Are you comfortable about how you would do the triangle bit? This is your fella, right? Now I want to describe this triangle. And I'm going to typically, I like to do the X's, so in this case from 0 to 1. And then I need to do the Y's. And to do that, don't we build a little vertical rectangle? And we find the equation of this line. Okay. What is the equation of this sloping line? Okay, let me ask different.
8x.
Shouldn't it be negative 8x plus 8?
Yeah,
Right.
it's the same thing.
Same thing, yeah. 8 minus ax minus a. So don't you find the slope of the line and then where it crosses the y-axis and you put them together? And that is what goes in here. Right, the bit I'm not going to do in any great detail is find out what z is. But if you call this guy P and you call this guy Q and you call this guy R, won't you find the vector joining PQ and the vector joining PR? Then you will find what's called the normal vector to the plane, which is you find the cross product of that. And then you do the dot product with n and x, y, z, and it will be the dot product of n with any one of these 3 guys you like, but I like the first one, so I will do that. And won't that generate your equation? Now, the equation that you get won't be this one, but pretend it was. It's going to be 3x plus, I don't know, 2y minus 4z equals 10, right? It's going to have that kind of look to it. Then won't the last step to be to solve for z equals? Are we comfortable with this vague process? Since I'm not giving you too much specifics because I want you to actually do one from as much as you can from scratch. Now, again, we'll keep it vague. Suppose you're told the surface is this guy, and it's in the first octant. We want to find D. Right? We want to find what does it look like and how we can set it up so we can do our double integral, right? What's the general way that you tackle these types of questions when you're trying to find D?
Typically, you just solve for Z and go from there.
Oh, that would be for the GXY bit, yeah. But if you just want to find out what D is, don't you make Z one particular number? That's what I'm getting.
0.
You make it 0. Now, when you make it 0, do you see you now know what D looks like? Now, if you draw the line x plus y equals 4, it looks like that. But the line continues forever, except they told you that. So do you see it's now just that triangle there? Because if you're in the first octant, does not mean x and y are positives. If you're wondering, and I've just thought of this, and it's really hard to draw this, but I'll try my best. If you wonder, how do they name the octants? Then this region over here is the first octant. This one over here, it's hard to draw, but this one over here is the second. This one is 3, and this one is 4. Can you imagine the top floor? You go anti-clockwise, 1, 2, 3, 4, right? And then you go on the floor, right? And the floor would be 5. You can't really do it. Underneath that guy, 6. Underneath that guy, this guy here, 7, right? Underneath the last guy, 8. So you go on the top, you can imagine the top, it looks like that. And then underneath it, I don't know, does that help? It's really hard to draw a 3D thing in 2D paper. But I don't think we've ever done a question where it wasn't the first octant. So you're probably never going to need to worry about, oh, it's in the 7th octant. But I guess you could figure it out. Now, in this case here, then, don't you put your classic vertical rectangle? If you can possibly do it, I suggest you make the x's zeros to the number. In this case, what's this equation of this line?
Y equals 4 minus x.
Now, for the G parts, and someone did mention that's a good point, to get the missing G function, don't you have to find out what Z is in terms of X and Y? And we'll assume that it's positive. Well, based on the first octant, I'm sure it is. Right. That would be the Z that you would need in your equation.